Thank you very much, and thank you very much for the nice introduction. And I also, thank you very much. Thank you very much for the nice introduction, and I also would like to express my gratitude to Professor Inguscio and Professor De Nicola for inviting me to this very special occasion, to this very special and exciting place. It's a great honor for me to talk to you today. I was asked to give you a presentation about metrology and chemistry and biochemistry and the areas which need to be addressed in this field. And so this will be a broader approach, and I will be talking not just about food issues but also about health issues, which is a particular issue for us to work on at the Physikalisch-Technische Bundesanstalt, the PTB in Germany. And before I go into such details, I would actually like to start with an example which comes from the food area. And I hope this will be working now. Yeah, fine. So metrology is all about global comparability, comparability over space and time. And in order to clarify that and why it needs to be global, I would like to come back to an example which goes to back to the days of my childhood. Actually, in those days, there was an advert kind of going through the television in other places in Germany, which was very popular, which said "Aus deutschem Land, frisch auf den Tisch," fresh from German countryside onto the table. So it was about food. And actually, though this was very popular at that time, it actually completely disappeared. Nobody is talking about it anymore. And this is not only because the taste of the people actually switched since that time. And I think we have more Italian restaurants in Germany than German restaurants in the meantime. But this is actually not the only issue. And there was a little scandal coming up in the year 2007, which I would like to use to explain what I'm talking about. And there were some headlines in the newspaper which said dioxin in German yogurt. So there was still the talking about German yogurt. And at that time, it seems weird to everybody how the dioxin actually came into that yogurt. And so it was investigated in more detail, and then it was actually found that a part of the fat in the yogurt was replaced by guar gum, which is an emulsifier, and people don't want to eat so much calories, so they replaced the fat by the guar gum. And it was a guar gum that contained that dioxin. And then you may ask the next question, where is the guar gum coming from? And the guar gum actually came from Switzerland. Interestingly enough, it's probably not what you expected it to come from. And they looked in this thing a bit more in detail and more closer, and then they found that there was not just dioxin in the yogurt, there was also PCP in the yogurt. And now this starts to make sense, because the PCB is a fungicide, and dioxin is known to be a byproduct of the production of PCPs. And this is the very reason why PCBs are actually banned in Europe for 20 years already. And at that time, it became clear that the company in Switzerland that imported the guar gum to Germany actually obtained the guar gum from India. And now this becomes a full story, and it tells you that we are looking at an industrial product. It is not just that there is a cow which you milk and you bring the milk to a dairy and it produces some yogurt from it. It's much more complicated. And this is a development that we also see in other areas of industry. When you buy a car, whether it's a Fiat or a Volkswagen, you will always notice that it contains a large number of parts which come from all over the world and end up in one product. And the food industry is actually not different. So we also have products which are composites of things which come from all over the world. So they're nothing anymore like German yogurt or anything like that. So that tells you that we need a lot of understanding and measurements which go on a global scale, also in the chemistry sector and here, particularly in the food sector. Now there are some lessons to learn from this which go on and over that, and is that life and well-being as well as international trade require internationally comparable measurements, also in biochemistry, and that needs to be on a high level to detect toxins like dioxin. But it is not just that. There's a speciality which comes to the whole business in chemistry, in this chemistry sector. When you go onto the market and you buy a kilogram of apple from a farmer which is there, and you look at the bag that he gives to you and the apples inside, you might actually look at it and argue, well, it doesn't look like a kilogram apple that I asked for. It's not a kilogram. And the farmer will probably answer, of course it's a kilogram. And then you can at least drag your your balance, your spring balance out of your pocket, and you can weigh it, and you can make an argument about that. But when it comes to chemical measurements, you don't have such an option. Chemical measurements cannot be carried out by the customer, the taxpayer. And here in particular, you need an international infrastructure which assures that the products which come onto your table and which you eat and affect your health are actually healthy. That is a very particular issue. We completely depend on other people, and that makes it so important. So similar quality standards must apply for chemical measurements on a global scale with respect to the traceability to the ESI, the measurement uncertainty, and the detection and quantification. These are the kind of things that we need in order to make a proper quantification comparability of chemical results. Standards must be maintained over an extended period of time. That's the other thing which comes on top of that. I just said that PCBs are not permitted anymore in Europe since 20 years, but nevertheless they appear on the market, and it just doesn't only apply to PCBs, but also to a large number of other products. The problem that we have in the chemical sector are further reaching, however. So we want to realize, maintain and disseminate national standards, just as in the physics area. But the problem is that the number of products that we have in the chemical, or the number of measurements that we have in the chemical sector is extremely large. We are talking about millions of analytes in hundreds of different matrices that we have to look at. So when I look at the situation in PTB, you can see that in PTB, most of the units that we have in the physics area are actually covered by national standards in all necessary and important measurement ranges with the required measurement uncertainty. And in the chemistry sector, we are never ever able to achieve that. We have to address this problem in a very different way. We will only be able to provide national standards for a very limited number of analytes. So we have to make choices. And that means that we have to have a strategy. What are actually the things that we are looking at? And this means that we have to concentrate on certain things. And the decision that we took was to concentrate on the life and well-being of the general public. And this concerns areas like health, environment, and food. And in fact, it is not just us who do that, it is the areas which are dealt with in the consultative committee for the amount of substance in metrology and chemistry of the meter convention. So this is something which happens on a global scale. And also, when you look at the research strategies of a number of countries, you also find these issues there on the top of the agenda. And what concerns all of us is what happens in the European Union. And we have as a strategy the Horizon 2020, and these issues, health, environment, and food, are also on the top of the agenda in Horizon 2020. Except for preparing national standards, we also disseminate these standards to the end user level, which are usually testing laboratories in the field of chemistry. And we all know that it's a fairly easy task when you look at the dissemination of time, for example. So there are atomic clocks at some places in the world, like Braunschweig and in other places in Italy and elsewhere. And when you want to know the exact time, then you look into your computer or the telephone line or the television. They will tell you what the time is based on the atomic clock that there are. And of course, in chemistry, this is more difficult. So what we do is we use reference materials which can be sold to those testing laboratories, but in order to assure that they all measure correctly, we also carry out proficiency testing schemes, and the vast amount of the work is actually done by accredited calibration laboratories which carry out such proficiency testing schemes with large number of laboratories. And of course we need to integrate that all into a global accepted infrastructure, which is the meter convention. There's nothing which is outside of the meter convention separately available in the chemical sector which compares to the meter convention. So it's very important to link to the meter convention as well. So having said all that, we have at least a little bit of an idea what metrology in chemistry and biochemistry means and why we need it. And I would actually like to switch now to a work example, an application case, which shall tell you how the whole thing is interrelated to reality in the moment. And I will now switch to an example which comes from the health sector. And as I said, this is because we are working in this field quite strongly. And I would like to confront you with a situation that we all come through at some part in our life. We go to our doctor and have a blood sample being taken from us. And this blood sample is usually not investigated by our doctor, but it is actually sent to a clinical testing laboratory. And we also would like to have a confirmation of our status of health, of course. But apart from that, we might also have a number of other questions, such as the time when I get the result. We don't want to wait for very long. Also, we all pay a lot of money for our health insurance, and so we want to know as to whether that is expensive or not. And of course, we want to know whether the results are actually reliable, because otherwise it is completely useless, and we really want to know that. So that's the most important bit of all of it. So then we are waiting for a while, and then we get the results, and the results may look like this. So this is the answer which I got from my doctor at some point. And he said that your cholesterol level is too high. The results from the testing laboratory shows that you are some 10% above normal area. So here you are. So what does it mean? Is the result true? What is measurement uncertainty? You can already see these are the nasty questions a guy like me would ask my doctor. And would I get a different result from a different testing laboratory? Is it medically relevant? So you probably don't ask your doctor for such questions, because you will probably not know an answer and will be upset when you ask questions like that. So you go back into your office and you think about that in metrological terms, and you look at numbers, because we are metrologists, we like to look at numbers. And then concerning the cholesterol, you might find the results of a field study, which was carried out in the United States of America at the Mayo clinics, and they investigated some 20,000 people concerning their cholesterol level. And the first thing that you can notice there is that the situation is already very different from that what you see in many other areas of physics, for example, because what you see is that the spread of the data over 20,000 people, whether they are healthy or ill, covers a range of a factor of 3. So now when you compare that to the physics area, for example, electrical resistance measurements, and you can see that the differences you observe there go over 10 orders of magnitude. So in here you got stuck with a factor of 3. And all the decisions a doctor will take depend on the results which he can see and obtain within this factor of 3. So what does it mean in practice? So there has been a decision limit introduced, at least in the United States, which says as a doctor you should act when the cholesterol level is at above 240 milligrams per deciliter. So when you look at that, then you can think about the results that has been measured from you or from somebody else. And this tested results might have shown 240 milligrams per deciliter when it was actually only 220 milligrams per deciliter. That means that already 20% of all patients would have been treated when it was unnecessary. And treating high levels of cholesterol is possible by medical treatment, but it might have severe side effects, like losing your memory. And on the other hand, you might be exposed to a heart attack when levels which are too high are not treated, and when the value is 10% lower than it should have been, so it shows 240 when it was actually 260, then 13% of all patients are left untreated, which are pathological. So these are the consequences, and this is difficult. You see the differences are small. And then you realize that this study has been made in the United States. And you might actually ask the question, do people in the United States measure in a similar way as we do it here in Europe? Can we actually extrapolate the results from the United States study to Europe? And I will show you later on that this is actually not the case, as you might be surprised to hear. So, what shall we do? What we see is the result accuracy is important, and we need to take care that the measurement results are correct. So, this has been recognized by the politics, and the politics give some rules which should assure that the measurements which are carried out in the clinical sector are correct. So we can be happy about that because it's important. And that what applies to all of us is the In Vitro Diagnostica Directive of the European Union, which says that all measurements that are carried out in the sector of clinical chemistry must be traceable to higher order standards. That's what it says. It doesn't go into more detail than that. So how this is implemented is actually a question which is then solved in every country in Europe in a slightly different way. But it has been made in a very elaborate way in Germany and ended up in the directive of the German Medical Association. And when you look at this directive, the Richtlinie, then it has actually an appendix. And this appendix contains a number of analyses. So, let's imagine the situation that we have in the clinical sector. You have more than 1,000 biomarkers, clinical biomarkers, which are of relevance and which are tested from time to time for various reasons. And we can impossibly provide standards for 1,000 analytes. So, the German Medical Association has taken the decision to make a shortlist. This is a list which contains some 40 analytes. And that's what we see on the next slide. This is an extract of that list. And when you look at it, you see several analytes there. And let's have a look at one of them. So that's uric acid. And the values that are obtained from a clinical testing laboratory should be accurate within plus minus 13% from a reference method value. So that's RMW in the end. So when it says RMW, reference method value, then it means that we will have a national standard for it, and it will be traceable to this national standards. It should not deviate from this national standards by more than 13%. You can also see that there are some analytes for which there is no reference value, so it says SW, and I will explain to you a little bit later what that means and how we deal with that. Now, how can we assure that the results of the clinical testing laboratories are actually really within this 13%? So we have a hierarchy. We have a traceability chain, and in this traceability chain we have the medical testing laboratories, and there are more than 1,000 of those testing laboratories there in Germany, and they obtain a sample from a serum pool which comes from a reference laboratory of the German Medical Association. That's on this level here. And they send these serum samples out to those 1,000 test laboratories, and they have to report back a value which they obtain with their methods. And these reference laboratories provide a reference value for this serum pool. And then they have to agree within this 30% with this value of the reference laboratories. And these reference laboratories are actually accredited as calibration laboratories according to ISO 17025 and 15195. And in the course of this accreditation process, they carry out comparison measurements with us, the PTB at the top level, and we have to have more accurate measures than the accreditation laboratories. So I have a great admiration for that, what the people in the testing laboratories do, because it is worth seeing their work and going there and having a look at it. They sometimes have to investigate some 10,000 samples a day, and they must make sure that none of them is exchanged for another one. And they have to act very quickly. So when they do a measurement of cholesterol or uric acid, they have probably 5 minutes time and a budget of €5. And the results must be correct within the legal limits. So the other thing is that when you go there and they are located in a big clinical hospital, they also have to assure that they provide a result within 30 minutes. So sometimes when there are emergency cases, they have a special unit which provides those results within 30 minutes. And they must be correct within the legal limits. And in order to assure that, you must be prepared beforehand. You must know whether you can achieve such results. On the second level of the accredited calibration laboratories, they have to be able to produce these big serum pools and to send it out to those testing laboratories 4 times a year for proficiency tests. It's also something that we cannot do on the uppermost level of the National Metrology Institutes. So everyone has its specific role in this traceability chain. And of course we have to have the most accurate methods and must be very accurate, and that costs money. It's very expensive what we do. So when you look into detail, you can find that the chain looks like this. So the test kits have to be accurate within plus minus 13% in case of cholesterol, or uric acid has to be the same for those cases. And what the people use are usually test kits, immunoassays, photometric methods. In the level of the accredited calibration laboratories, they use higher order methods. That's spectrophotometry, chromatography. Sometimes they use even primary methods like mass spectrometry and so on. And so they have to reach a level of plus minus 5% roughly. And we use primary methods, and with these primary methods and primary tools, isotope dilution mass spectrometry, I will explain a little bit about that later on, we can achieve an accuracy of, say, 1%. So this is what our traceability chain looks like, and I will show you a little bit with one example what that means in practice. So here we go. And the accuracy of 1%, why are we arguing that we can achieve 1% on the primary level? This is because we carry out so-called key comparisons on a global basis. And this is an example, one of the first ones that were carried out on cholesterol. And we have several results reported back here from various national metrology institutes, like the National Institutes of Standards, or the INRIM in Gale, or from Japan and China, and so on. And you can see that in spite of this being a global exercise, when you use primary methods, you can actually achieve that there are more or less within 1% of results, sometimes 2%, but 1% in general. So these blue bars here indicate plus minus 1% for those results, and the bars here, the vertical bars, indicate the measurement accuracy that was predicted by the various national metrology institutes. So that works quite well. So let's have a look how that looks in case of the clinical accredited calibration laboratories, and they use so-called Newton diagrams to show what their results are. That is a very useful tool, and I will very briefly explain to you what it means. So we have a sample A here and a sample B. So they don't get just one sample, but 2 samples. And what we can see is that there is a reference value here that was in this case produced by us. And this reference value says, and here it is measured in millimoles per liter, don't be confused by that. It says that more or less the reference value is 3.6 millimole per liter for sample A, and it is some 4.8 millimole per liter for sample B. So this is our reference value. So we participate in this scheme of the reference laboratories to provide a link to the SI by participating in it and knowing how accurate we can measure. And then you see that there is a spread of the results produced by the accredited calibration laboratories on a global scale. So this is a global proficiency test for calibration laboratories. That's something which is very unique, which we only have in the clinical sector and which we should have in other areas too. And we have this because there is a joint committee for traceability in laboratory medicine, which is a joint venture of the International Federation of Clinical Chemistry, the Meter Convention, and the International Laboratory Accreditation Corporation. And so it's something the whole world can relate to, and that makes the work a lot easier, so that we can test all of them at the same time. Now you see several samples and the spread of the results which we have there. So we say an accredited calibration laboratory has to be within 5%, so it looks like this. This is a 5% bar. And you can see that there are some results which don't really go into this 5%. It's there in the upper left. And those results up there. And when you look at it in more detail, you can see that those results, which cluster around the reference value, are produced by mass spectrometry, a primary method. And the other results which are there are produced by spectrophotometry. And this method is actually called the Abel Campbell method, which is a very established method for a long time, and which is used by reference laboratories in the United States as a reference value. And you can see here that the results which they relate to are 5% different from the results that we have in Europe. So this is a little bit annoying for our colleagues from the National Institute of Standards in the United States, because they also use mass spectrometry, of course. But this is a reality. So that's what they do in the United States. And so there are reasons to be skeptical as to why if measurements carried out in the United States are the same as the one that we carry out here or carried out in Asia. It is an important issue. And when you then apply all this to the testing laboratories, and these are the results of the proficiency testing that was carried out in Germany. So there were 1,300 laboratories participating in this proficiency testing scheme. And what you can see here is the reference value, which is there right in the middle at 2.5 millimole per liter for sample A and some 2.4 for the sample millimole per liter for the sample B. And the diameter of the spot indicates the measurement uncertainty of that spot. And the black square that you can see here are the legal limits. So these are the 13% I was talking about earlier. And you can see that the testing laboratories in the field were using 3 different testing methods. And one of them were producing results which are systematically too high, and the other one results which are systematically too low. So this test was actually already quite some years ago, and the consequence of this test was that the testing methods, which are here indicated in red and blue, disappeared from the market. They are not there anymore. And this due to the traceability of the values. And this kind of service is something that we provide for, as I said before, most of the analytes which are on this short list of priority analytes. And with them, we can cover some 70% of all measurements that are carried out in the clinical sector. So it makes sense to reduce this number from 1,000 to 40, because we can really work with it, and it's a pragmatic approach to make tests for most of the analytes of interest in the clinical sector. And because that's the case, a similar approach could be applied also in other areas of chemistry and biochemistry, and that's indeed the case. And this is just an indication that laws which are relevant for making correct measurements are not only there in the medical sector, but they are also there in the environmental sector when it comes to measurements of water or air. And they're also there in the food sector, for example, when it comes to measurement of residues in food. So we have regulations for that in Europe too. So those residues are very often antibiotics, for example, because it is very dangerous when we eat antibiotics and become resistant to it. The reason why there are antibiotics in food is that we have industrial livestock feeding very often when it comes to chicken or other things in Europe as well as in other places in the world. And because of this industrial livestock breeding, the likelihood that there's a transmission of diseases among this livestock is very high. In some cases, the farmers give antibiotics as a precautionist measure to keep the animals alive, but this is of course not permitted because of these dangers of taking up antibiotics for human beings too. And this is why it is prohibited, and that must be controlled, and that's regulated also in the Commission decision 2002-657. And also in there you find exact regulations which say you should be investigating a number of antibiotics, and the list is again some 30, and the measurement ranges and the accuracy is exactly defined. Now, this is something where we also wanted to build up a hierarchy, as we have seen it in the medical sector, but here we have actually been asking one of our partners to collaborate with us here as a designated institute, taking up the role of a National Metrology Institute for us, because we simply didn't have the workforce to do the work on our own. So we have asked the Federal Institutes of Consumer Protection and Food Safety, the BVL, to do the work for us, and we approached them and said, we think we can provide metrological traceability for your measurements, and they were very excited about it, because they said, we don't have internationally comparable values, and that's a big problem because there are a number of countries who export goods from other parts of the world into Europe, and they just fail to import these goods because they don't know anything about our regulation and how to measure them. So what we did was to carry out measurements together with them on chloramphenicol, which is one of those antibiotics, and have tested them in buffer solutions and milk and in tissue, and we have learned a lot about food analysis, which we didn't know before, and they learned a lot about metrology they didn't know before. And when we had all that achieved, we went to the meter convention, CCQM, and asked them to carry out a pilot study on such kind of measurements. And that was a start at the beginning of measurements of residues in food at the meter convention on a metrological global level. And when we looked at the result of the first comparison that we did, you can see that although this was started here in Europe and in Germany, there was a lot of interest for such measurements on a global scale. So there were partners from China, from Thailand, from Mexico, from South Africa, and many other places. And they achieved a reasonable agreement. It's a very low concentration level, so it's not as accurate as it is in the medical sector, but it is quite accurate. And what you can see here is that we carried out the same comparison with the same samples with the official residue control laboratories that we have in Europe. And what you can see here, the result is that they both came up with the same value, more or less, but the spread of the data is much smaller, nearly 10% between the National Metrology Institutes compared to the official residue control laboratories, which had a spread of 30%. So, interestingly enough, it turns out those residue laboratories can also measure obviously correctly, but they don't know how correct they can measure, because there's a lack of understanding of metrology. And this is a kind of information and message that we can pass on to them, that they can do much better if they would look more closely into metrology. And this is one of the messages today, that it is very much worth it for them to get metrology involved and understand what they do. Now, from this point onwards, I want to go on and talk a little bit about future tasks as well. So where are the areas that we need to address and understand a little bit better? And I would actually like to return to the priority list that I showed you before in the case of the clinical sector, and talk about those things which are then at the bottom and which don't have a reference method value. So that's HCG. You can see that the uncertainty that they have in the moment is much bigger than that we have for other analytes, and it has a so-called set point value. So the point is that those analytes are also important. So some of you might know this is actually used in a pregnancy test, and there's no such a thing as a half pregnancy. You are either pregnant or not. You really want to know that, so we need accurate measurements in that field too. So what's the problem with this kind of analytes? The problem is that they are big. They are much bigger molecules than the uric acid or the cholesterol that I was talking about earlier. So these are proteins, large molecules. And the problem is that the mass spectrometers of today won't be able to measure them just as they are. So that needs to explain a little bit what we do in case of a primary measurement method. So in isotope dilution mass spectrometry, and this is really a very simple sketch, what we do is the following. You see the analyte up there on the left-hand side. This is cholesterol. That has a molar mass of some 386.7 grams per mole. And this is the thing that we want to measure. And we measure it by adding an internal spike to the serum. And this spike is also cholesterol, but that's isotopically exchanged. So some of the carbon in that cholesterol is changed, and C12 is replaced by C13. And that changes the mass, so it's now 388.7 grams per mole. And we add a known amount of that spike to the serum. For example, 1 gram. And in the mass spectrum that we get then, we have a peak of the unknown at a mass of 386 grams per mole, and a mass of the known spike, this 13 carbon labeled cholesterol. And we can work out how much of the unknown cholesterol is in there from the ratio of the spikes. Now, this is a simplification. Then what we really do is more complicated. It's called exact matching isotope dilution mass spectrometry. And I'm not going to explain that in detail because it's just would cost us too much time. But this is enough to know that bit from here. And as I said before, that is not simply extended to large molecules because the masses would be so big that we cannot distinguish between the signal of the spike and the analyte of interest anymore. So, but those analytes are measured. So how are they measured? That was usually done in a normal clinical laboratory. Looks like this. They use an immunoassay. And when you use an immunoassay, you have an antibody, that's a red dot there, and that antibody has a so-called key, and that attaches to the target molecule. So it's a key lock system. And if the key and the locks are very well defined, then you get a color reaction when they combine, and you can quantify the reaction product. So if that works fine, then you get a good result, but in a very large number of cases, you have so-called cross reactions. So what happens then is that you have a second protein which has a similar lock, and then the antibody gets attached to this kind of different protein as well, and then you get a cross reaction. And if there is a different producer of a different immunoassay, you might actually get an immunoassay which gets attached to epitope 2, and then the result will be very different. The consequence of this is that the results that you get in case of important markers might be different by 1 or 2 orders of magnitude. So this is an example of troponin. Troponin is an indicator of a heart attack. When the doctor finds some troponin in your blood, he can expect that you get a full-blown heart attack within a few weeks. So the detection of troponin might save your life, and you really want to have accurate measurements there. So what can you do? We need a primary method for that. That is our target. That's our challenge. So we have small molecules like the cholesterol, and the other one in this case is C-reactive protein, which is an inflammation indicator, which is 1,000 times bigger. So we have to do something about it. And the approach that we followed in PTB for solving such a problem was to cut down the protein, to cut it into pieces. So we make an enzymatic fragment, and we look at so-called peptides. Peptides are here T6 and T12. And those are the ones which we also label isotopically. So that gives us T6 star and T12 star. So those peptides have the property that they are only occurring in this protein of interest. In this case, we have taken growth hormone as our guinea pig because it's easy to handle. That's where we tested it. And T6 is a part of that protein, and it is a specific part. It is a fingerprint of that very molecule and nothing else. And then we can quantify this peptide instead of the whole protein. So we cut down the protein to size to quantify it. And by doing that, we find a primary method for quantifying proteins if we have a characteristic protein fragment, which we have in a large number of cases. Not in all cases, but in a very large number of cases. And what we get then looks like this. So we are back to our Newton diagram with A and B, and this is a result that we obtained in one of those proficiency testings for growth hormone in Germany, just in the same way carried out as it was done for cholesterol in the past. And now we have a reference value, which is due to isotope dilution mass spectrometry because of that peptide route that I just described. And what you can see is that the results that were obtained from the testing laboratories spread over a wide range. So you can see there is this wide range of results from here to there, and they cover the whole values that are physiologically possible in a human body. So basically, the message is that there is no medical information in these immunoassay results. And you need to put some medical information into it. You can do it by applying the primary method. So when we look at these results in more detail, we find that several different test kits were used, and some of them produced results which were significantly higher than the isotope dilution mass spectrometry primary value. Some were lower, and some were very close to the real value. So for the first time, they have a reference point which is traceable to the SI for proteins. And this is the kind of work that we need, that we have to develop methods which also allow to quantify traceable to the SI large molecules like proteins. And this is an issue which doesn't only apply to the medical sector, but to other sectors too. But I would actually like to take this opportunity to show you what you can do with this kind of a method, because you can apply it to other fields as well in a very efficient way. So we have a European Metrology Research Program project running at the moment, which is on metal proteins. And a very famous metal protein, which we all know, is hemoglobin. And this method can actually be used to make very interesting measurements on such hemoglobin. So first of all, hemoglobin is one of the important priority analytes, which we would like to measure very accurately, but it's not only that. You also have to distinguish between different forms of hemoglobin. And this is actually a problem, which I describe to you now, where we were pointed at from one of our accredited calibration laboratories. It said, well, we have a problem here, and we need you to solve this problem. And this problem is new in Germany. And I will explain to you as to why this is the case. So hemoglobin is a large molecule, a large protein, which contains 4 sub-proteins, smaller proteins. We call them globins. And hemoglobin contains 2 alpha globins and 2 beta globins. And this hemoglobin A0 makes up some 95 to 98% of all hemoglobin in our blood. But there are other forms of hemoglobin as well, namely A2 and F. So F occurs in little babies when they are born. It's not so much of an interest in the moment, but there is this A2 form as well. And this A2 form contains the globin delta instead of beta. So beta is replaced by delta. And the consequence of that is that the hemoglobin is not working very well anymore. Hemoglobin contains the so-called heme group. This is this blue little thing here. And this blue little thing contains iron, and the iron is responsible for the oxygen exchange in the blood. And with a delta instead of a beta globin, it's not working very well anymore. So when you have too much of this A2 version in your blood, you become ill. And the illness is called thalassemia, which is Greece and stands for the Mediterranean illness. And the reason why it occurs in the Mediterranean region is that it has some advantages too, when your level is something in between the normal state and the ill state, namely the borderline cases, which you have then in this case of some 4%. And in this case, the result is that the number of red cells produced by the body is increasing. And that protects you against malaria. And that's why it is prevailing in those countries where malaria is important. Now, there is no importance of malaria in Germany, but we have a lot of people coming from other countries where malaria is important. And this is why the number of cases of thalassemia were also increasing in Germany. And this is why it is a problem now and was no problem in the past. So we are developing new methods for hemoglobin A0 and A2 to quantify these values of A0 and A2 and to understand that a little bit better. So we were pointed to that by our colleagues from the Accredited Calibration Laboratory Instant in Düsseldorf, and they connected us to Professor Mosca at the University of Milan in Italy for the work on these kind of things. Now, we are now also working on different methods which go in the same direction, quantification of metal proteins. So we are using, for example, also species analysis, where we separate the protein and quantify only the metal content of the proteins. 1/3 of all proteins contain metals. And so this is a kind of species analysis. And we are doing a lot of work on that, not only in this project, we have other projects which also involve INRIM, for example. So these are the groups from Dr. Maria Paola Sassi and Dr. Michela Sega. And we also use a completely different method, which is also based on isotope dilution, which is Raman spectroscopy, which we also want to use for quantifying proteins, and we have some collaborations with Dr. Andrea Rossi in this field here, also from Europe. Now, this also gave you an overview of the things we need to do in chemistry and biochemistry, and I want to conclude now. And I want to do that with giving you an example of what the future challenges are, which we also have to look at. And for us, it means to go to even bigger objects, not just only proteins, which is our main part of the work, and most of the work is not done yet. But in the future, we will also have to look at even larger objects like viruses and microbes and bacteria. And I will give you one reason as a conclusion why we should do that. And this is a case which occurred right next to our doorsteps in Braunschweig some 3 years ago, and you might remember it. It has certainly gone to the newspapers here in Italy too. There was the outbreak of EHEC, which is a special form of Escherichia coli bacteria, which causes some diarrhea. And we had an outbreak with some 3,000 cases in Germany in 2011, almost exactly 3 years ago. And 900 of those people developed the HU syndrome, which means that the people also obtained a kidney failure, and in the vast number of those cases, people who survived it need a kidney replacement after that. And we also had some 53 death cases. And the reason why it occurred, to find out about that, was extremely important at that point to finish off this disease. And it's a big crime story behind that. It involved our partners from the Federal Institute of Consumer Protection and Food Safety. And it turned out that these bacteria were located on soybean sprouts. And the soybean sprouts came from an organic farm, which is just 30 kilometers north of Braunschweig. And the reason why they had this EHEC was because they imported seeds from Africa. And this EHEC was actually coming with these seeds to Germany. So that's how complicated the whole story is. And this is why it is so important for us to develop methods for those larger molecules, starting from proteins, over viruses, over microbes. So there's still a lot of work to do, and it is essential for us and for our lives. Thank you very much indeed.